webinar on solving the interconnect density bottleneck in 51.2T switches. Thank you for joining us today, May the 4th, Star Wars Day. This is the 10th in a series of webinars presented by COBO, the Consortium for Onboard Optics, and sponsored by DuPont's Silicon Valley Technology Center. In this webinar series, we've really been looking at the future of the data center. And in that domain, the role of switching really is at the heart of the matter. With the first generation of 51.2T switches running at 100 gigabits per lane now on the horizon, the market is really starting to consider the pros and cons of different board designs for managing so many high-capacity channels. So will co-packaged optics or near-packaged optics scale to meet the bandwidth density challenge? That's our topic. In this 1-hour webinar, we're first going to hear from Dr. Rebecca Schaevitz, who is a board member of COBO and a principal engineer and product line manager at Broadcom. Then we're going to hear from Tom Mitcheltree, advanced technology manager at US Conec, which is a supplier of connector embodiment packages based on standardized and custom optical interconnect ferrules. After the presentations, we should have 15 minutes or more for Q&A. So your questions really are welcomed. Please use the Q&A function below and not the chat function, and we'll answer as many of the questions as we can. This entire webinar is going to be available later as an archived video, so feel free to go back and look at it a second time or share it with your colleagues. And with that, I think we're ready to begin. Rebecca, the floor is all yours.
All right. Thank you so much, Jim. It's a huge pleasure to be here today. As Jim mentioned, I work at Broadcom, and I'm both a product line manager as well as a principal engineer for silicon photonics. I've been at Broadcom since the start of the silicon photonics generation here. And what I'll talk about today is scaling into the next decade, using highly integrated silicon as the building block of the future. Before we get into that, of course, there's a reason why we want to scale. Data centers themselves are growing dramatically, and we can look a little into history and see how that growth has skyrocketed. We're looking at something like over $100 billion of CapEx spend by the cloud with a 15% year-over-year growth. And if anything, the pandemic has taught us that that growth is accelerating even further with our need to connect. And with that comes also a lot of data processing and data movement with over 20 zettabytes of cloud data movement. That's something that my brain can't even wrap around that scale. And of course, if we bring that down into an individual hyperscale data center, that's over 100,000 servers, over 10,000 switches. And of course, you need to start connecting all of these. And we're seeing optics becoming the dominant connectivity solution with over 1 million optical interconnects in a given data center and growing. And that's huge. And we can also look at the future, right? Where is this going? Light counting has shown that in 2021, we're about 3% of the market is used in high performance computing and AI clusters. And that area is expected to grow to over 50% in the next 5 years, which is huge. And that's a huge change in the architecture and how things are connected, as well as the number of interconnects and semiconductors being used in that space. Of course, with that is also a similar growth of the cloud DC switches growing from 17% to 38%. And that's a huge area of connectivity. We can look at this as well in a different way, looking at the semiconductor utilization in the IT infrastructure space being almost 25%. So, this is the motivation here, right? We're seeing new architectures. We're seeing new needs for connectivity as a result of those new architectures, and both scaling out as well as scaling up. In the AI ML space, there's a lot of scale out as well, a lot of nodes that are needed, in addition to being able to scale up in the bandwidth that's being utilized. Of course, all of this is great. The demand is great. We want more and more optical interconnects to go into the field, and that's fantastic. However, how do we connect everything? And right now, one of the biggest areas of connectivity still in the data center is electrically based, right? We have a lot of DACs that go from the servers up to the top of rack. And those DACs need approximately 2 meters of distance in order to make sure that the entire rack can be connected up. And as we go in speed from 53 gigabit per second today to 212 gigabit per second in the future for, let's say, 102 terabit switch, what we're seeing is that the loss is increasing. And this is known, right? This is not some surprise that's coming to us all of a sudden. But that loss is becoming insurmountable. And the industry today is doing a lot of things in order to try to overcome these losses. For example, we're doing flyover cables to reduce the loss that's going through the substrate onto the PCB and through another connector by mitigating some of that with flyover connector, which is great innovations in that space, but they're not cheap, right? They come at a cost. And that cost is both in the materials, in the processing, as well as in how you put things together, the assembly. And if we can't go 2 meters, or at least we can't go it without a dramatic increase in cost and complexity, then it makes sense to go into optics. And if we're going to go into optics, and now the server all the way up to the rack and above is all optical, it makes sense to flatten that curve, that power curve that we're using to deal with all of these losses by bringing optics closer. So another way to look at this same problem is kind of a top-down approach instead of that side view that I was showing earlier. So today we're taking a traditional transceiver. Let's say it's optical. Everything is now optical in this new world of higher speed. We have a DSP, we have drivers, TIAs, EMLs, PDs, all discrete components in a traditional transceiver. The largest component, about 65% of the power utilization within the transceiver is the DSP, trying to regenerate that signal and the losses that happen along the path from the core silicon through the package onto the PCB through a number of connectors. And this transceiver has worked really well up to today. However, if we're looking at the future and we're scaling into the future, the number of channels that are needed and the bandwidth that's needed, as well as the power consumption that can be realized within these racks, they all need to scale appropriately. And there's a huge challenge here if we're going to continue this, as I showed in that plot before on the amount of loss that we're seeing going this long electrical link. So if instead, we say, let's get rid of that long electrical link, let's bring that in to the core silicon package and co-package everything together, we can eliminate the DSP and we can eliminate a lot of those losses that we see going through PCB and connectors and have really the ultimate short electrical link that has the lowest amount of power consumption possible. And we use the same amount of power then to on the optical side to go into optics, and we've drastically reduced the electrical power. Also in this way, if you're using silicon photonics to do this co-packaging, you can get to the smaller form factors that allow you to scale in the same way your core silicon is scaling in the channels and the bandwidth, as well as in the power consumption, as I mentioned. Lastly, you're removing a lot of components, connectors, DSPs, and things in the path that bring cost into the picture. And so you can also drive that cost down. So if we look at this in a more numerical sense, right, what are the actual numbers that we're seeing if we do this co-packaged solution and we truly bring all of the optics onto the same package as the core silicon? The first thing you can look at is the channel and bandwidth that I was talking about, so the escape density. If I look at a 3.2 terabit solution, so a 3.2 terabit tile, let's say optical tile, and we go from a front panel pluggable density to a CPO density, what you'll see is that we'll get about a 5x improvement in the overall escape density. Now you can go even further than that if you add in wavelengths. For instance, if you go into an FR-based solution in which there's 4 wavelengths, you can then get a 20x improvement in the scaling. And if you go in the future and you're going beyond FR, perhaps FR8, 8 wavelengths, then you can scale to something like 40x improvement in the overall density of the solution, which is huge. On the other side, you can also look at the amount of power, right? So the other advantage here, as I mentioned, is you're removing all of these electrical interconnections and losses due to long trace lengths and going through connectors. By eliminating that, you can get something like a 4x improvement in the amount of power in the package. We can also look at this a little bit maybe more discrete in a sense of the history of using transceivers and compare it to a given transceiver. So if we look at a 400 gig, 800 gig, or 1.6 terabit transceiver, what I'm showing here in blue are transceivers that are built with DSPs that are using the most aggressive node possible. So 5 nanometer, 3 nanometer nodes in order to drive the amount of power down. So this is an aggressive target on the amount of power consumed by a transceiver at 1.6 T being 25 watt. What I'm comparing to is CPO, in which it's a holistic view. So it's the entire optical apples to apples comparison. And you're getting over 50% savings using the technology node today at 7 nanometers. So that means we can save today what would be in the future for the transceiver, which is huge, right? That means we don't need to go to exotic processing. Cost is dramatically improved by doing so as well. So huge benefits for going into this. And I've spoken a lot about the why, right? The data center is growing, the different infrastructures for AI and ML. And I've spoken to, trying to migrate to CPO here, but how do we do this? How do we achieve these goals and these numbers that I'm showing here? And one of the things that you can look at is what the high bandwidth memory market has already done in this space. So in HBM, they've co-packaged multiple dies. In fact, really, really tall stacks of dies, skyscrapers of HBM dies on top of each other using through silicon via technology as well as micro bumps. And they had already met this same challenge of scaling in bandwidth and channel count such that they needed to co-package with things such as a GPU. And they did this starting about a decade ago, scaling into volume. And this is a very high volume process today. And it co-packages multiple dies with a common core silicon. And what we're doing co-packaged optics is really no different. We, in fact, only have 2 dies that are stacked on top of each other, an electrical and an optical die. And those 2 dies simply need to have optics to go on and off. That's the main difference here. Everything else is the same, especially when you put the laser outside of the package and you put it in the front panel. There's no light, in fact, on this optical engine. It is a silicon engine that's being co-packaged with a core silicon. And that's what we're doing at Broadcom. We call it Silicon Photonics Chiplets in Package, or SCIP. So our SCIP engines are these chiplets that are photonic and electrical IC that are stacked on top of each other. And they're co-packaged on a common substrate with a DSP in the case of a transceiver, and then with a switch ASIC in the case of a switch. These, of course, also need to be solder reflow compatible, where you can reflow that package onto a PCB. And lastly, as I had mentioned previously, you need the ability to do an optical detach. And this is important for handling and to be able to use all the standard CM type semiconductor processes, and then have the CM simply do an attachment of that optical interconnect later. And just as a comparison here, what you can see on the left is what was reported a decade ago by NVIDIA, showing HBM co-packaged with presumably a GPU. And today our SCIP engines co-packaged with a 25.6 terabit switch ASIC. Now you can see the density of all the micro bumps and the pitch in this space. And overall, the comparison is very similar between these two. And that's because we've designed it to utilize what's already gone into volume manufacturing. Of course, to achieve this, there's been a lot of innovations even within Broadcom itself in different pillars. We have some of the world-class ASIC capabilities in-house, along with mixed signal IC. On the optical devices, some of the areas here that we've been able to bring into the CPO world is our laser technology. I'll talk a little bit later about the advances in our laser technology and packaging that we've done in order to enable the best system level performance in terms of power and cost. Advanced packaging is huge. We already in-house do co-packaging of high bandwidth memory with core silicon. We've utilized that, and then we've added on capabilities such as our detachable optical connector to enable full semiconductor compatible processes. And lastly, silicon photonics, it didn't exist at Broadcom 3 years ago. We brought it into Broadcom and we built it up internally to have this core competency, utilizing really giants of the past in development to where we are today and being able to tip this off into a volume manufacturing process. So let's dive a little deeper into what this looks like. Right? I've talked through the why and the how do you do it, but how did we do it? And one of the biggest areas here in the skip technology is to have everything that is completely pitch matched to the very first IO, which in this case is a switch ASIC. So if we look closer and we zoom in on the switch ASIC and the pitch of the switch ASIC IO to our electrical IC IO, you can see that they're completely pitch matched. And that's important to get the lowest possible loss on the electrical link and be able to bring these parts as close as possible together and keep the smallest substrate size and the package size to stay within industry standards. The second area is the optics itself. So the optics needs to be highly dense optical components in order to stay within the same pitch matching. And then the connection between the optical chip and the electrical chip using the through silicon vias and microbump technology allows us to maintain that pitch match solution. And lastly, as I mentioned, we have the beachfront in order to get light on and off our chip. And that also has to match in pitch. And what we've designed is the equivalent of 5 MPO12 connectors in the footprint of 1 in order to maintain the appropriate pitch all the way from our switch ASIC through to the optics. And these innovations allow us to drive to the lowest power and highest density solution. And that's what we demonstrated at OFC just a couple months ago. What I'm showing here is our 25.6 terabit solution, our co-packaged optics solution, in which 12.8 terabits is optical and 12.8 terabits is our standard electrical link going to the front panel. You can see in the box image on the left side that we have in green our MMC ports by US Conec that are the highest density 12 or 16 port connectors that we can achieve. And then next to that is our remote laser module. There's 4 of them, each supporting 3.2 terabits of data to get to the 12.8 terabits aggregate. And then lastly are the standard pluggable ports that you see today. And you can see that it's much more compact on the optical side compared to the electrical port. And not only that, the design of the electrical port, it has to be as close as possible to the switch ASIC due to those electrical links that I mentioned earlier, whereas the optics are kind of free to roam about the country. They can go anywhere, and it's all dependent on simply the cabling infrastructure that you put within the box. So I've spoken a lot up to now about 25.6 terabit, but what about 51T, right? That was the premise of this talk here. And if we go to 51T, I've kind of done a simplified version of the standard solution here where we're using pluggable transceiver, and I've just stacked 2 25.6 terabit boxes on top of each other, but it gives you a sense of the scale. So if we look at some of the factors that determine how we scale, right, the density of the thermal and power, I'm not talking now in the case of the channel count or the bandwidth. I've spoken a lot about that already, but let's talk about density, thermal, and power at the box level. If we look at the traditional transceiver solution, you would need something like 64 800 gig transceivers, which automatically is a 2RU size. Or even if you said, okay, I can try to fit this into a 1RU using 32 1.6 terabit transceivers, the amount of power that you're talking about at the front panel, if you have 32 of these 1.6 terabit transceivers, if you recall, I had 25 watts for a traditional transceiver at the most aggressive node, is 800 watts right at that front panel. And that doesn't even include the amount of power consumed inside the box, right? The switch ASIC at 51T and all the peripherals that are needed. And the amount of cooling then becomes very challenging. So that thermal load is hard. And if you look at, what are the limitations of driving power into a rack or into an individual box, you might be exceeding that amount of power consumed. And those are all huge challenges in the transceiver space as you scale to 51.2T. If you look conversely at a CPO-based solution in which you're using 16 of our remote laser modules at 3.2 terabit each of those remote laser modules is about 8 watts of power. So that's 128 watts at the front panel, right? That's a significant reduction, 6x reduction in the amount of power used at the front panel. And with only 16 of these, it easily fits in a 1RU space. Now, the total power consumption is about 320 watts of optics. So about 200 watts more is in co-packaged with the switch ASIC. But because you don't have that large thermal load at the front, you can efficiently still cool and potentially get to that 1RU case. And overall, the amount of power consumed is 800 watts compared to 300 watts. And that's a huge savings in this space. But one of the other things I do want to point out at the box that is a little different as we go to a co-packaged solution is that we have our optical I/O ports at the front. And if there is any damage whatsoever to those optical I/O ports, you can no longer just throw away a transceiver and replace them. You do have to decommission the box or deal with the fact that those links might be down. I think it's an important opportunity that the optical space realizes that if we have an even more robust connector, and I know there's a lot of work going into, for instance, expanded beam connectors for single mode, I think those will be great in this space to ensure that we have an incredibly robust solution on the optical connector that matches the same reliability of the silicon that's inside the box. The second area of the front panel is the remote laser module. I've touched a little bit upon that remote laser module already. As I mentioned, it's only 8 watts for each of those, supporting 3.2 terabit with 8 lasers at 20 dBm of that power. That's pretty impressive, and I think world-leading numbers here. And we do this via an uncooled design. So it is a double height remote laser module solution, about 2x the height of a standard DD. So it fits in 2 of those pluggables. And we're able to do this effectively in order to drive the amount of power down at the front panel, as I mentioned, which allows us to reduce the amount of carryover heating of our switch ASIC, which is really important. And then once again, only 16 of these are needed and can fit into a 1RU space at 51.2 terabit. But one of the key areas here in order to realize these remote laser module solutions is having a blind mate connector. And it's blind mate, which is important for eye safety. It's kind of amusing that we use the term blind mate and eye safety in the same sentence here, but it is very important for eye safety that we don't have 100 milliwatt of power going outside of the box. And that brings us to another opportunity in this space that will really help drive the CPO ecosystem. So these blind mate connectors, they do need about 4 to 16 PMF fibers and many demate and mate cycles similar to standard transceivers today. But one of the bigger things about this, because MPOs can meet that requirement, is the fact that it needs to be both dust insensitive and handle these high powers. And by dust insensitive, what I mean is simply that if dust is present, you don't get a full failure of your system. And unfortunately, I think we've all seen this, that any dust or damage on a connector, the optical interface of that connector, plus 100 milliwatt of power is catastrophic failure of the connector at both ends, which would mean that you would have to decommission the box, open it up, replace the cable in order to solve the problem at the box level. So you really want a connector that can handle some level of dust and not have a catastrophic failure. Another aspect to that would be being able to go, for instance, to be able to hot plug or unplug this connector with fans blowing, right, where you cannot assume a dust-free environment. And one potential solution, right, that probably many people in the optics space think about when they want a dust-insensitive connector or even a damage-insensitive connector would be an expanded beam solution. And those exist, and that's great for the front panel, the I/O port that I mentioned earlier. However, in this space, many of those connectors that I've seen, at least, are plastic-based. And we know that plastic and 100 milliwatt of power can be very challenging to achieve over a lifetime and not have failures. So this must also have materials that can handle those 100 milliwatt or perhaps even 150 milliwatt of power in the future. So it's a huge opportunity for this space to really push forward in driving to new optical interconnects that really meet these challenges and make CPO ecosystem robust. And in doing so, we can take the skip architecture and bring it not just from the transceivers today and the co-packaging with switch ASICs, but we can meet those other challenges in artificial intelligence, machine learning, high performance computing that I had mentioned previously being a huge growth factor over the next 5 years. And we can help enable these XPU to XPU interconnects or resource pooling that would be phenomenal for optics to get into. So with that, with the skip architecture, we can deliver the disruptive system value of 30% power savings, 50% improvement in rack density, and a 40% lower optics cost per bit. And we're firmly committed at Broadcom in going into this direction of CPO and skip. We see the electrical links having the challenge. We see optics needing to enter into the field and a new network design in order to enable it. And with that, we've created over 10 unique blocks of IP. We have over 150 people dedicated solely to skip and CPO solutions. And we're working with external partners as well, over 15 of them, to drive these solutions into the market. And that's also why I'm on the board of COBO, is to make sure that we have a robust ecosystem for these solutions. So with that, I'll let Tom talk a bit about the optical interconnect side and where innovations are going there. Thank you so much.
My name is Tom Mitcheltree. I'm with US Conec, and as Rebecca mentioned, I'm going to go into detail on some of the optical connectivity considerations for co-packaged optics. So for folks that are familiar with fiber optic connectors, there's certainly a number of decisions that have to get made, and Rebecca did a nice job of mentioning some of those. She mentioned density, how many fibers can you fit per a 1RU panel. Granularity is a term that we use in terms of number of fibers per connector. I think most folks in the industry are familiar with terms like insertion loss and return loss for connectivity. But for CPO, there's going to be new terms like PER, extinction ratio for some of the external laser source connections. And then finally, and I think this is something that Rebecca just closed on, ecosystem. For fiber optic connectors, ecosystem means a number of things. So we'll go into each of these pieces of the pie here to make sure that if you're choosing a connector for CPO, you kind of have all the variables in mind. So kind of starting on the left-hand side of that chart, density and granularity. So again, density is simply the number of fibers that you can fit into a 1RU panel given a particular connector type. And I think most folks who have been paying attention to CPO know that for a 51T switch, you need 256 fibers for an FR, and 1,024 fibers for a DR switch. But you know, the fiber optic connector, the I/O, does not get all of that front panel real estate. It has to share that with a lot of other things, including, like Rebecca showed, the external laser sources, LEDs, and then of course any type of airflow that's needed to cool the components on the board. So for the sake of argument, we're going to assume that the optical connectors get 50% of the real estate for this study. And that might be a little generous, but it's just a nice round number to start with. And then in terms of granularity, you know, there's a number of fiber optic connectors on the market, of course, and each one, or there are several with different fiber counts. So the granularity is what we're calling just the number of fibers per connector. We're going to just assume a one-row connector, just for the purposes of simplifying installation and polarity. You know, we'll look at a one-row connector, like for instance an MPO16 or some of the other connectors that I'll show you in the presentation. So what we've done here is we plotted the connector density, so the fibers per 1 RU on the x-axis, and the connector granularity, the number of fibers per connector on the y-axis. And we kind of set some targets for FR and DR. You'll notice those are about 256 fibers for FR and 1,024 for DR. But like I mentioned in our assumptions, we're going to assume we only get 50% of that space. So we're going to move our goalposts out a little bit here. And those are the targets we're actually trying to hit in terms of density for each of the different connector types. So to walk folks through the types of connectors that are commonly used, I think everyone knows SC and LC. Obviously has been in the industry a very long time. Only two connector or 1 or 2 connectors per fiber if we're talking about duplex LC. So not very high on the granularity, but also not very high on the density. You can't fit a whole lot of those onto a 1 RU panel just because they're relatively large. That's what prompted the development of a connector like MDC, which has about 3 times the density of duplex LC. And so that starts to look like a good solution for perhaps an FR panel. Then you get into the MPO connectors, MPO12 or MPO16, 1 row. It seems like if you had 50% of your panel, if you could dedicate that to optical connectivity to the I/O, that would be ample. For DR, probably not. And then you've got the 2-row connectors for MPO, MPO 24 and 32. Those start to look like better decisions for DR. But again, some folks may want to go with a 1-row connector to simplify, for instance, polarity. And that's where something like the MMC connector, a 16-fiber connector all in 1 row, really has density that's, you know, quite literally off the chart here. But also has a granularity that's not too high. There's not too many fibers per connector, so maybe more palatable for the industry. And that's a physical contact connector. Traditional connectors, very similar to MPO, as I'll show. But then there's also, as Rebecca mentioned, there's expanded beam technologies out there. So MXC, whether it's an MXC 16 fibers per connector, or an MXC 32, those start to become you know, options for CPO type applications. So taking a closer look at the switch that Rebecca just showed us, as she explained, half the ports on the demo are electrical pluggables and the other half are CPO. So overall, the front panel real estate is somewhat comparable between the two. I think the electrical pluggables take up a little bit more real estate than the CPO, but it's comparable. And within CPO, really the majority of the real estate are the external laser sources. They're larger modules, and you know, just need that area on the front panel. So what that really drives is the need for a very small optical connector, a very dense optical connector. And we feel that you know, what we call these VSFF, or very small form factor high density connectors, such as MMC, really start to make sense for CPO starting around 51T. You know, you can see in the brackets there, or within the arrows, I guess the green connectors on the far left, the MMCs, that's 256 fibers. So it's 16 fiber connectors. That's the same amount of I/O in terms of fiber count as what would be, and if these were optical pluggables, if we pretend these were QSFP-DDs or OSFPs, you would consume 256 fibers over a much, much bigger space on your panel. And the MMC, for folks that may not be interested, or maybe may not have heard of it before, is our very small form factor. That loosely stands for, the way we kind of remember, is the MMC. The second M is for multi-fiber. It's based on our MDC connector, which is what loosely called mini duplex connector. So they share the same connector housing, or a very similar connector housing approach for MMC and MDC. But the ferrule, the part that holds the fibers, where the fine alignment occurs, is much different. As you can see on the right, the MMC, which is drawn to scale here, is based on an MT ferrule. It's a much smaller ferrule, but it's based on an MT type ferrule. Where MDCs, we leveraged existing ferrules for LC, 1.25 millimeter ferrules for LC. So in both instances, we took something that was successful and folks that are familiar with and comfortable with, but really tried to slim it down, tried to take away some of the unused space on the MT ferrule and try to take the LC ferrules, in the case of MDC, and put them in a smaller package such that we could increase the density. And across the bottom there, you can see that. So what we call our ferrule inside the MMC connector is the TMT, or tiny MT ferrule. And what we like about it is it's the same pitch between fibers, it's the same pitch between pins, it's the same diameter pins and pinholes as MT. So it's 16 fibers at a 250 micron pitch. It's intermatable with MT if you wanted to do that. But it's also compatible if you want to use fiber sizes that are smaller than a typical 250 micron OD. So if you're going with a smaller OD fiber like 200 microns or 165 microns, our TMT ferrule, our MMC connector are compatible with that. And so Rebecca also mentioned expanded beam, and there's a few developments here that I want to make sure the industry is aware of. One thing is that for single mode performance for expanded beam, it's really starting to approach what we've seen traditionally for physical contact connectors. The target loss and return loss, you can see there, is around 0.5 dB for insertion loss, 55 dB for return loss. That's much better than where we were a few years ago with the technology. It continues to improve. As I showed on the previous slide, or a couple slides ago, something like the MXC32 has density that's very comparable to MMC. So in terms of getting the numbers of fibers per 1 RU, expanded beam can be a very dense connector as well. And it can be dense because it can hold a very high fiber count. Expanded beam connectors don't need physical contact of all the pieces of glass, all the strands of glass within a ferrule. It just needs to touch at about a 3 Newton spring force. So it uses the same spring force regardless of the fiber count, which allows us to get to some pretty high fiber counts, pretty high granularity. And again, as Rebecca alluded to, it's also expanded beam connectors can be easier to install or service because the beam is expanded. The spot size is larger, and it scales at about a factor of 25x or so in terms of insensitivity to dust. And then lastly, the single mode fiber expanded beam industry is based on the multi-mode variant that's been out there for a decade or so, with millions deployed. So this isn't something that we're starting from scratch. It's always good to have something that the technology is based on. So one of the things that Rebecca mentioned earlier was connectivity to external laser sources, and as an innovation opportunity. We see power density as one of the largest driver, if not the largest driver, of potential failures for an ELS connector. So how big is the spot size of your light, and how much of that is power being distributed across it? If you've got a 9 micron fiber, that's a lot higher power density than you would if you expanded it out to a 50 micron beam or something like that. So again, the power density reduces by about the same factor of 25x that we talked about earlier for dust insensitivity. There has been some encouraging initial results for initially just putting polarization maintaining fiber into physical contact array connectors like MTP or MPO. So making sure that we got the clocking correct, we get a good extinction ratio. That's the graph on the right, and the picture on the bottom shows that we are able to get PM fiber into MPOs. And there's also some encouraging results on getting high power through on single mode fiber through an expanded beam connector. So not using PM fiber yet, that's the next step, but just base single mode fiber and going with some, getting into the hundreds of milliwatts. The initial results are looking encouraging there as well. Definitely more study is needed, just getting started with this effort, but we are putting energy into this, and specifically not just the feasibility of it, but the optimization of it, of the termination process for cable assembly houses, and the manufacturability. And then also working with the industries to make sure there is a clear understanding of what the threshold is for the amount of acceptable debris in the laser path. That could be much different than the existing visual inspection criteria that's been in the industry for a couple decades in terms of the amount of acceptable debris for a normal data path connector in terms of insertion loss or back reflection. Another thing that single mode expanded beam enables is separability at the optical engine. So for some of the CPO discussions that are going on now, sorry, I just caught a typo there. So for some of the optical engines for today's or upcoming co-packaged devices, the optical engines are connected with a socket, but future ones may require that being soldered to the host board. So if you have your optical engines soldered to the board, you have to have some type of separability for manufacturing and everything else. So you definitely don't want fiber that's relatively low reliability hanging off of an ASIC that's a high dollar, high reliability type component. So being able to disconnect your fiber from your optical engines from your ASIC may not be something that's needed right now for initial CPO devices coming out, but it may become a necessity in the future. So we are putting energy into both edge emitting and surface normal, as we show surface normal on the right here, methods to provide that optical separability from the engine. And just circling that here below to make it clear what we're talking about, that connection from the engine to the ferrule that would eventually take the fiber out to the front panel. What we show on the right is a US Conec single mode prism light turn. So it's an 8-fiber light turning device that couples light coming surface normal from an engine and couples it into the ferrule where it turns at 90 degrees into a standard 8-fiber ribbon, 250 micron pitch ribbon, and then can take it out to the front panel. So, I think what it comes down to is just some decisions that we're helping the industry make by enabling some of this newer technology. So if you look at the difference right now between single mode fiber physical contact connectors like MPO and MMC and single mode fiber expanded beam connectors like MXC, the insertion loss, the return loss, the technology maturity, those right now are all in favor of physical contact. I mean, physical contact connectors have been in the industry for 20 plus years. There's billions of those deployed. It's just it's a good thing that we have that to leverage in the industry. But expanded beam is catching up. Like I said, the losses are coming down. There are novel ways that are being considered to lower the return loss to make it closer to what return loss is for physical contact. And again, it's single mode fiber expanded beam is emerging, but it is not starting from scratch. It's leveraging a multi-mode fiber expanded business that's been out there for a decade or so. At the same time, physical contact just isn't standing still. We are continuously trying to reduce the insertion loss for physical contact connectors. In fact, there's a path right now to try to get to lower losses beyond quarter dB for physical contact. But if you look at the bottom half of the table, that's where, things like expanded beam really start to shine when you talk about sensitivity to dust, dependence on cleaning, those kind of go hand in hand. Spring force for being able to do, high density connections, and then power density, the potential for lowering that power density to perhaps help for a high power channel. Those are all things where expanded beam can help. And then lastly, getting into the ecosystem part of the pie chart that we showed at the very beginning, having a connector portfolio or family that can solve a number of problems is going to be, I think, important for CPO, because there are a lot of different design approaches in terms of not just the connectivity at the front panel and what connectors folks use and what fiber counts folks use, but whether they need a mid-board connection, whether they need fiber on the back plane. If all of a sudden your front panel gets very dense, then perhaps fiber on the back plane is something that people will be interested in. And gained insertion, just with a lot of smaller connectors, it might lead to the need for some way of ganging the connectors together for mass insertion and mass removal. Between the VSFF like MMC and the expanded beam family of connectors, those are all options that are available to those technologies. And then lastly, for the ecosystem, it's more than just coming out with a new connector style and calling it a day. For us, that's just the beginning. We realize that we have to enable a global supply chain. So, we never develop a connector without coming out with termination tools, polishing fixtures, cleaning and inspection equipment, installation tools, all the hands-on training that is given to the industry so that it can scale, and not just locally, but dozens or hundreds of cable assemblies across the world. So it's important not to overlook that part of the equation, because that's a substantial amount of work that goes into introducing a new connector into the industry. So just to summarize, again, when selecting or considering a connector for CPO, density and granularity are obvious. And our point here was just to inform folks that there are newer connectors coming out that are physical contact, expanded beam, that are very dense, and that can solve the front panel problems that CPO presents in terms of the amount of fiber needed at the front panel. The performance physical contact continues to improve, the losses continue to come down, and expanded beam is doing everything it can to close the gap. The ecosystem, again, more than just the connector itself, we're trying to enable options at all parts of the link, whether it's at the front panel, as we traditionally think where optics live, but also midboard at the optical engine, or even off the back plane. And our goal is, as connector manufacturers, is to make sure that we're training and ramping and scaling a global supply chain. And then finally, expanded beam, like both of us mentioned, there may be a lane here for expanded beam to solve a lot of problems that folks haven't traditionally thought of for pluggable solutions, but that may exist for CPO. The fact that it eases installation, enables things like blind mate connections, and then again, it reduces the power density, is all promising things for expanded beam, and again, something that we continue to put a lot of energy into. And that's it. I appreciate your time.
Below, we have about 15 minutes, and I'll read as many of these questions out anonymously as I can. We'll capture all of the questions, and we'll ask the speakers to get back to the ones that we didn't have time to answer. So with that, let's jump in. Rebecca, we have a question, our first one. You said eliminate the DSP. If that's the case, where's the chromatic dispersion and polarization mode dispersion and equalization done if there's no DSP? And what about FEC coding and decoding?
So I am definitely not an expert in this area. So I'm a principal engineer in the optical connector realm. So I will answer as best as possible, but happy to have a follow-up if you want to email me and I can direct you to the right resource. The essential thing is, if you can, on the electrical side, right, if you reduce the link sufficiently, then you're not going to get any electrical dispersion going into your optical engine. After that, we do still have TIAs, and we have laser drivers that handle a lot of the analog components to make sure that the optical performance is good going and meeting the standards on the optical side. I think anything more in depth than that is not my realm to answer, but happy to direct that person to the right contact.
Okay, great. There's a couple more for you, Rebecca, before I'll direct some to Tom. But the next one is, I think, your comparison with a high bandwidth memory. What is the max clock rate for use in DRAM chips? And do you know if the optical transceivers need much higher speeds? So basically, is that comparison between the two of them?
What I don't know that anyone can say a max rate of anything, given the fact that electrical keeps chugging along and optical does too. What we're doing today, is 50 gigabaud to get 100 gigabit per second of PAM4 technology. We do think this is scalable to the next generation of speeds. I'm not gonna, once again, this is not my core competency, and I don't want to misstate anything. Happy to answer more questions and direct to the right people within our organization in this space. But we do think it's overall scalable, that there is a solution. And if you go into silicon, there's a lot of other ways in which you can also ensure that you have good signal integrity to drive the solution based on where you place different IP blocks in a co-packaged space.
Okay. Rebecca, there's a couple other coming in questions about Broadcom skip. So I know you had a couple of slides about that, but maybe we could turn to those.
Sure.
And I think, Tom, you have to let her be the presenter again. So the question is going to be about the skip. I think that was like slide 13, somewhere like in the middle of your presentation.
The main benefit is just the high speed line that we're talking about, right? It's going to go, instead of having to go through silicon via all the way up to the photonic chip, you're going directly into the electrical chip. So that reduces your overall link length, turns in the electrical line, everything that can create loss or other signal integrity issues like crosstalk. Ultimately, it's literally the shortest link you could possibly have, and thus drive to the lowest power and best signal integrity.
Okay. Do you consider parallel IOs for electrical links between the die? That would save tremendous amounts of power.
So essentially getting rid of the SerDes and going to lower. Mm-hmm. It's definitely a possibility. It's something that would require even further network change and innovation in the pitch matching, really. That I think it's open field to look at that. That's just not what we're driving to today to meet the market demands.
Okay. There's another question, skipping ahead a bit, and that is going the same one on power efficiency. And I think that may have been like slide 8 that you were looking at that. Yeah. So the question is, could you please elaborate more on the power savings you'd expect from CPO and where they're coming from? Are you assuming a linear link for the ASIC to engine link, or are you assuming an XSR? Are there any sources of power savings when you compare the CPO with traditional transceivers?
Sure. So, I'll first go into what we're doing and then how it compares to maybe an XSR-based solution. So what we're doing is we're taking a standard switch ASIC, and we're taking that LR, MR, SerDes, short reach SerDes capabilities, and we're using it as is, right? So we're powering it down. We're using only the number of taps that we need in order to drive our optics, and we're bringing our optical engine as close as possible in order to make that efficient. So that allows us to leverage the switches that are on the market already today, And that's huge, right? If you want to talk about cost savings and scalability, we don't need a dedicated switch ASIC tape out to do what we're doing here. The second part of that question is, how does that compare to XSR, and what components are removed? We are driving directly. We're removing a DSP in the path, and we're driving our TIA and our laser driver, and our TIA goes directly into the SerDes that's combined with the switch ASIC. An XSR type model, you would need the equivalent kind of symmetric solution in which you have some of the signal integrity regenerated on both sides. So we are kind of one-sided in that case. XSR is great, and you can drive to low power as well in that system, but you do need a dedicated switch ASIC to get the lowest power on the switch side and achieve the same power results that we're doing by using a common standard switch.
Okay. Could you comment on thermal managements of the CPO package?
In terms of thermal management, we're not doing anything exotic. We're using the same capabilities that are used today to cool, even 351T. It's not any liquid cooling or anything. It's a standard air-cooled solution. So it's relatively simple in the sense that, we're only adding a couple hundred watts to the package. And I say only, but it's not that much compared to some of the other solutions that have been spoken about in the market. And our front panel is also far less dense in terms of thermal load, right? So I mentioned the remote laser modules are 128 watts. And that's in comparison to something that would be equivalent of about 800 watts, the front panel. And so overall, the thermal is manageable in that case using traditional thermal solutions. Okay. Yeah.
One more question on this slide. The total power consumption of that 1.6T transceiver, does that include the ELSFP power or just die and package substrate?
So in terms of the 1.6T CPO equivalent, it absolutely includes everything. So it includes the laser, it includes the optical engine in that path. If you look at a system level, you can go even further than that, which we don't necessarily include here, but we're bringing down the drive on the switch ASIC because we're only driving directly to a very short distance. But this is just apples to apples comparison, assuming nothing changes about the switch itself.
Okay. A couple more questions for Rebecca, and then I'll jump over to Tom. So does the 8 by 100 milliwatt ELS laser with 8 watts of power consumption imply a wall plug efficiency of 10% under worst case conditions?
I have to go back and remember what the wall plug efficiency conversion is there. So I'm not going to answer that right away. But I think you can calculate that pretty straightforward, right? It's 8 watts for 8 lasers with 100 milliwatt of power output. Okay.
All right. So let's give a couple questions over to Tom. So first, Tom, what is US Conec's timeline for single mode expanded beam connectors?
Yeah, so for both single mode fiber expanded beam and for the MMC connector, we're sampling those now. So if folks are interested in samples, want to see how it performs, just contact us.
Okay. And expanded beam is in the middle of single mode light path. Is there any expected optical signal integrity issues or any test with digital traffic through the high order modulation such as PAM4?
I don't think so. We haven't seen any difference in a PAM4 signal versus a regular, PAM2 signal for these types of links. Now that may change once it's converted to electrical, but I think in terms of the passive optical connection, we're not seeing any difference.
Okay, and maybe we can pull up the slide you had where all the different connectors are being compared.
Sure. Yeah, just give me 1 sec here.
And the question really here is going to be about the cost of connectors with PMF. Will they scale in volume, or is the cost limited by more involved, the more the involved alignment needs to be?
Yeah, so certainly everything will scale with volume. Initial connectors, any technology, I guess, when it comes out, if it's trying to compete with an incumbent technology with a lot of volume, then that's there may be some type of curve at the front. But that's part of the reason, Jim, that we really try to leverage existing technology. So again, the MDC that we showed leverages the same LC ferrules, those same 1.25 millimeter ferrules. The MT ferrule, the TMT ferrule that we have for MMC leverages the same approach as MT and the same molding techniques. It's just that it's into just a smaller package. So absolutely, we're trying to do everything we can to leverage existing technology so that the cost is not prohibitive.
Okay. Could you go up to page 8, please? And there's a question on your ER definition.
Okay. There we go.
Yeah, so could you explain more about ER?
Well, I might have to defer to our test folks for that one. The extinction ratio that we were working on with a partner to do this research, the bar for them was fairly low, more like in the teens. So we did not get very granular with our extinction ratio definition here. We saw that it far exceeded what they had as a target, and that was enough for us to move on, and at least from a feasibility perspective, say, okay, this looks like something that is possible. But for a more in-depth discussion on how we measured extinction ratio and what that means, I'd encourage folks to reach out to us so we can go into more detail offline.
Okay. Tom, is a light turning expanded beam connector preferred for saving space, or a straight through expanded beam connector?
So most times a light turning type connector is used to couple light off of something that's on the board. So we've been doing light turn in the multimode space for about 15 years, and it was used for onboard optical modules like Snap 12 modules and before that. So typically when you're trying to get board off of a dense area on a card and then take it to the front panel, we would use the light turn type device. When it gets to something like a front panel and it's a more traditional type connector where you're just trying to basically introduce what some folks still call like a mechanical splice, just a traditional connector, then the edge emitting or the front emitting type connector is typically what's used.
Okay, great. And we're really just about at the top of the hour, so I'm going to give the last question to Rebecca. And could you tell us a little bit more about the product plans or availability of Broadcom Skip?
Sure. So overall, this is coming to market with key customers that we're partnering with this year, and it's gonna maybe be more generally available starting early next year to others that are interested for 25.6 terabit, and then a year following approximately for 51T.
Okay, and in terms of ecosystem development, how do you see that playing out?
Oh, absolutely. So we are also working on our Skip engine itself and being able to work with partners, for instance, in the AI ML space on co-packaging, or even in the future in the NIC space, right? If we're bringing opticals all the way down to the server and co-packaging with different NICs, and creating a standard footprint that allows us to do that. And perhaps allows us to also open it up as an ecosystem. We do know that the more players involved, the more robust the ecosystem is, and the greater the market grows too, and that's important. Also on the remote laser side, it's important to also make that a standard in the future so that multiple players can play either inside the remote laser or in the packaging and creation of the the outline, the cage, and the actual pluggable. And those are all areas that are going to be important to have a good ecosystem moving forward. And I'm excited to be on COBO to help drive that.
All right. Well, excellent. Well, thank you, Rebecca, for presenting today. Thank you, Tom. Really glad to have you here today. Thank you to our audience for joining. We have captured all the questions, and if we didn't get a chance to address them at the end of this presentation, we'll follow up. This webcast will be available as an archive, so that video should be out in a couple of days. And finally, I'd like to thank COBO and DuPont Silicon Valley Technology Center for supporting this webcast. So thank you everyone for joining us, and see you next time.